Okay. All right. Welcome back, everybody. I hope you've enjoyed your coffee break. It's time for us to draw our almost last, but not last prize. I think we've got two more after this one. So welcome Lykourgos Mostopoulos, who is the head of R&D at nokia-hellas. So we're giving away a Nokia phone. Who is the lucky participant? Let's see. 3, 2, 1. Hit the run button. Τα έχουμε πει αυτά. Total winners 1. Nikolaos Vathis. Is Nikolaos here? No? Is he here? Next one. Are we sure? Okay. Final chance. Nikolaos Vathis, are you here? Nope. Let's hit it again. Konstantinos Douvaras. Okay. Next one. Okay. Run. Thanos Giannopoulos. Thanos Giannopoulos is definitely here. Έλα, Θάνο. Πώς. Δεύτερο δώρο. Ωραία. Come and grab it. Come and grab the phone. Thank you very, very much. All right. For our almost final keynote, can I welcome on stage Neal Norwitz from Google USA. Neal has been a software engineer at Google, working on google.com and youtube.com and many, many other things that I'm sure that we've all used or will be using in future. Welcome to Athens. Is it your first time in Athens? Fantastic. Welcome to Athens.
When I was preparing this presentation, several people said that I should introduce myself. Hi, I'm Neal. How many people have heard of me before this conference? Raise your hands. There's a few. I think the advice was a pretty good idea. So, before I get started, what you should know about me is that, like Steve, I'm old. I've been writing code for over 40 years. I've been doing software engineering for over 20 years, the last 14 of which have been at Google. I became a core committer of Python, like Benjamin, back in 2002 or so, though I was only active for about 5 years. So like I said, I'm old. And perhaps one of these days, I'll have some words of wisdom. But until then, let me tell you my story with Python. It began in the Python 1.2 days, and for those of you that don't remember the versions of Python, that was 1995. I started working on an air traffic control messaging system with a small team of about 5 to 10 engineers. Our goal was relatively straightforward. It was to create a product bringing SMS to air traffic control systems. And at the time, this was very novel. Air traffic control systems then, and even largely now, are primarily based on voice. And so using computers to automate some tasks could provide a very big win for both the pilots as well as the air traffic controllers. But the question is, how should we go about doing this? And my beginnings with Python started with a conversation I had with a colleague. And it went something like this. Eric said, I'm going to use Python to generate C code for the APIs. What's Python? It's a new language. Why do you want to use that? Because I don't want to implement over 300 repetitive APIs and make lots of mistakes. I can automate this task. Whatever, dude. As long as I don't have to write it, I can breathe a sigh of relief. I'm okay. Wait a second. We do code reviews. I'm going to have to read and understand this Python code? I don't even know what it is. So that's going to mean I'm going to have to learn it. Okay, fine, I'll learn it. Then came the question that always comes up. So you're telling me that white space is significant? Yes. Why? Well, it avoids redundancy because you don't have to have white space and curly braces. You already use white space this way. Why do you always need the curly braces too? Okay, that sounds reasonable. I guess I'm saying it's kind of weird though. And so when I look at Python, this is some of the first code that I saw. And you can see some of the things here. This is my first impression going back almost 20 years ago. And we see that strings are built in. But if strings are built in, why do you have to import a module? This is back before Python 2.0, when you got strings as real first-class citizens with methods on them. And what's up with those 3 types of quotes? You got rid of 2 types of strings, characters and strings, or character arrays and strings, but now there's 3 types of quotes. What's going on here? And print's a statement. Okay, that's fine, but whatever. I don't use print that much. And at the time, print was a statement. As I think Steve pointed out earlier on, print has since become a function. Python has moved on quite a bit from 1995. So my first thoughts about Python was, it's a nice toy. I've got C and C++. These are fine tools. I can also use shell scripts. What else does a real programmer really need? So Eric goes ahead and implements these APIs in Python. And the bottom line is, it actually worked pretty well. It automated this relatively straightforward task, and we were happy. Maybe, just maybe, Python was a little bit better than I originally thought it was. But it still didn't seem like a general purpose tool to me. Some years later, I started doing Java 1.1 when it came out, and this is about the year 2000. And Java is all the rage. There's a huge amount of hype around Java. People are saying it's going to be the last language you'll ever need or want. And I think, wow, I'm really excited. I'm going to join the startup. I'm going to do Java. I'm going to be happy. World is going to be good. Life is going to be good. Java will be all I'll ever need. Be careful of superlatives. The reality set in when I started doing Java after a few months. The performance was horrible, especially with the startup of the JVM. There were tons of APIs to learn, and it made simple things very difficult to do, and it should be the opposite. A language should make difficult things easy to do. The tools were immature. Developing in Java in 2000 really just kind of sucked. It was a huge letdown for me, and one of the most shocking parts of the whole thing was how gullible I was to believe all of the hype. And so I learned to not believe the hype so much and do some more investigation myself. Since then, again, this was 19 years or so ago, Java's come a long way, and most of the issues that I mentioned have been addressed. So the startup wasn't really going anywhere. I needed a break from work. I was just tired of it. I wanted to do something different. I planned to take several months off, give Python a serious try for a personal project that I was doing. It was nothing special, just a little toy for myself to say, okay, I tried Java, that didn't work out. Maybe I should be a little bit more honest with myself about Python and give it a try. And wow, it actually worked pretty well. I was really surprised when I gave it an honest try that it was easy. But my break only lasted for about a month before forming my own startup. I could fail just as well as other people can. And I did it with a colleague who had introduced me to Python. The previous company that we had worked at, where we did the air traffic control system, wanted us to do some contract work for a new application they were thinking about developing. So why not use Python for this new application? We set up a fixed-priced, fixed-schedule contract. It was going to last for about 4 to 6 months. We planned monthly demos to show the progress. We were midway through the contract. We had already given 2 successful demos. We were feeling pretty good, that things are going well, and we're pretty happy. The customer was also happy, which is the bottom line when you're doing this sort of thing. And then came demo number 3. the customer asked me to see one of the features that we had developed. And I went, sure, you press this button here and nothing. I thought a window was supposed to show up. I sheepishly say, yeah, it was. Why did everything go away? Well, I was blushing a bit at the time, I'm sure, and I say, I'm sorry about that. There's clearly a bug. We'll fix that for the next demo. So what was the bug? Really simple thing. We do refactoring a lot, doing software engineering, and you can see on the left-hand side the code that I had, and on the right-hand side the code that I changed it to. And I forgot to test the code. That would have been nice, except I didn't even have automated tests at the time. This was something that I learned later. It was really embarrassing, and I never wanted to repeat that again. So I thought to myself, can obvious bugs in Python code be prevented? And static analysis was relatively new in the mainstream at the time, and a lot of people thought, this is Python. What do you expect? You just have to run the code. And to be honest, I really expected something that would prevent me from making stupid mistakes like I did. Sure, I should have tested the code. Sure, I should have run the code and things like that. But there should be tools that can help me. Why didn't they exist? So I start my third Python application in a year. It was a science experiment. Is it possible to use static analysis on Python code? And again, most people said no at the time. They didn't think it was possible. I actually didn't even think it was possible. But I wanted to give it a try. I figure, why not? I've got some time. It will be fun. And I might learn a thing or two along the way. So to determine the answer, I had to really learn Python and try it for myself. So this is the sort of code that I was playing with. I went into the interpreter. The interpreter is extremely powerful. Many languages don't have an interpreter, and it makes it much, much harder to try things out, to play around, to see what works and what doesn't. The iteration cycles are much, much longer. But in Python, you can just type a few things into the interpreter. And if you can read through this code, and this is the sort of code that I wrote at the time, again, so it's Python 2 rather than Python 3, you can see that you can define a function that calls another function. Foo is defined and calls bar. You can print the type of foo, and you see it's a function. Wow, that's pretty neat. You can get the types of everything. Everything is an object in Python. And you can use dir, the built-in method, built-in function, on foo. Foo is an object. And you can see what are the other attributes of foo. It's a function, but it has a lot of other information, meta information about it. It has the name of the function. It has the docstring for the function. And you also see something in there, globals. Now, dis is a module in the standard library, and you can disassemble a function or a module or lots of other things. And in this case, this is the actual disassembly from within the interpreter. And you can see that it's a very simple state machine that is stack-based. And the very first thing it does is it loads global bar. So I can see that bar is the name of the function that is used inside of foo. But is bar in the globals? And you can see from the last print statement that it's not. Well, aha! You can find some basic problems and perhaps avoid a few embarrassing moments like I experienced. But then the next question is, but how many things can you actually find? So the real question is, when I started my third application, that was PyChecker, and I figured out how much I could do, and you can see how much was done. Now, it isn't perfect, but it can do a lot. This gives you an idea of how many warnings, problems, messages, some stylistic, some actual bugs in code that could be found. And this was, I don't know how long I worked for it, probably a couple of years on and off. It was just a spare time project. But there's a lot that could be done. But the implementation of PyChecker did leave some things to be desired. It's not perfect. It's not even close to perfect. There are lots of limitations. The code must be imported with the way that I implemented PyChecker. I did it how I showed you before with using the dis module and things like that, the tools that are built into Python. I did not go over the Python source tree. I did not parse the Python code at all because I figured it's changing a lot. I don't know how far this project's going to go. I have to get things to work, and so I'm going to take the shortest path possible to see if it was possible to actually do some static analysis. There was also no branch analysis. So ultimately, this means that a lot of code can't actually be analyzed using PyChecker. All of these problems can be fixed, but at this point, I don't have the time and energy to go along with it. There are other people that are still working on PyChecker. I never actually upgraded it to work on Python 3 since it works on the bytecodes. Some of the bytecodes are different in Python 3. It won't totally work today, but it still might kind of work, and I don't know what other people have done with it. But the effect of PyChecker was really quite large. Lots and lots of people used it. Lots of people emailed me and gave me all kinds of stories about how it helped them and did different things. And it felt great. I was really happy. It's open source. You can go out there and find it today. You could go modify it today. I use it on my own code. And so I found lots of problems in my own code. That was the original genesis of it. That's what I wanted to find. But I also use it on a lot of other code too. As I said, other people use it on their code. I use it on the Python standard library. And when I used it on the Python standard library, I thought the standard library was pretty good at the time. Did a lot of things, had batteries built in and all of that. Good. But I still found tons and tons of bugs that were latent inside the code. I'm sure people were running into these things. Sometimes they'd file a bug report, sometimes they wouldn't. But none of these things were actually fixed, and so PyChecker gave me a way to fix a lot of the problems. And after I did this for a little while, Guido said, hey, why don't you become a Python core committer? And I think, why not? Then I can fix even more problems. So I sunk a lot of time into Python, and it was a lot of fun. I like doing open source. I believe in open source. I thought Python, at this point, was a pretty good language. It wasn't necessarily my primary language, but I still used it often for everywhere that I could. And I kept finding more and more problems and kept fixing them, and then I would add more things to PyChecker, and I would get PyChecker better. And it worked great. So then Python 2.4 comes out around 2005. I got tired of my own business. About every 5 years, I go through this cycle where I'm bored with things, I need to make a change, so again, I make a change. Take a break from my own business. We had other people that were working there. They continued the business, which continues to this day, but I needed something new. I'm going to take another break, but then I'm going to join Google. They actually asked me to join them, which is shocking. I don't know how I got through the interview process. Like many people, it was just kind of crazy, just question after question after question. And really, most likely, the reason why I got into Google, or a big part of the reason why I got into Google, is not because I did well on the interview, but rather because they saw all of the work that I did over the many years working on Python and working on PyChecker. So I actually took a break this time. I took off for 2.5 months or so before I started Google. I kept saying I wanted to go longer, and then I'm like, okay, I'm done, I'm ready to start. And it was great. Google was a crazy place in 2005, and I mean that in a very positive way. There were tons of things going on. It was a very interesting place. It was a great place to learn, and for me, learning is very fun, so I was enjoying everything. Google uses its own style guides for all of the languages. So there's, well, not quite all of them, but almost all of them, certainly all the major ones. So there's probably about 20 different style guides, one for each language. C++ has one, Java has one, Python has one. So I figure, well, I've got to learn it. I've got to write code like this. Google also does code reviews, like we did in my previous company. And so you have to conform to these rules, and the style guide is the way to conform to them. That's what the rules are. So I start reading the Python style guide, and this is what I see. And my first thought is, oh shit. How did PyChecker get noticed by Google? How did I not know this before joining Google? And I think, oh my God, I'm in trouble. What the hell did I get myself into? My second thought is, how do I get myself out of here? If I leave now, is anybody going to notice? What should I do? So I take a step back, I take a breath, and then I think, what can I do? In reality, there was no problem. There was nothing I could do to change the reality. This is what it was. Yes, I didn't know about it, but no big deal. All of my previous responses, they were all very emotional, and they really weren't helping me in any way. So I just had to put them to the side. I had to say, life goes on. I'm going to survive this. It's kind of like preparing for a presentation. Everybody gets nervous. They come up here, and then they just figure, okay, I'll survive. So be realistic, be practical, and just accept, okay, it's a little bit weird, but one of the tools that I wrote that I didn't think was as big as what it was, I come to Google, it's this incredible company, and they're using it, and it's the #1 rule in the style guide. It's the first thing that I read. So I put it to the side. I go about doing my job, and then I do a bunch of different things. And by now, Python 2.5 is out or coming out. It's 2006, and I'm working on the Python C interpreter a lot. I started implementing a C abstract syntax tree API so that PyChecker itself could be implemented very quickly because the Python-based AST was immensely slow. It took like 2 minutes to process very simple Python code, where the C API would do it in about 0.1 seconds. And so having the C AST API would allow me to go on to do PyChecker, even though I never did, and fix some of the limitations that I had hoped to fix. I worked a great deal on the Python 2.5 release, wrangling it, getting things out. Anthony Baxter did a lot of the release work itself, but I made sure that the bugs were there and worked on the schedule. You can find my name in several different PEPs, including the Python 2.5 release. I tended to work on bug fixes, performance of Python, portability of Python, and lots of little things. Again, it was really just I was just scratching an itch. It was just something that was fun for me, and so I did whatever I felt like with Python. And it felt good because I knew a lot of people were using it, and it was very useful. I like the software that I write to be used and useful, and Python certainly fit that bill. So over the years, I work on various different projects at Google, and I use C++, I use Java, and I use Python. For this time, I spent most of my time doing C++. And at the time, the builds were slow, iteration was slow, velocity was slow. Google has an enormous C++ code base, and it's very intertwined. There's lots of legacy and lots of room for improvement, as there always is in any large software system. And I hate slow development. I hate going slow on anything. Velocity is really important to me. I think that if you can improve velocity, you can get orders of magnitude of benefits out of the work. You can just do different things if you can develop quickly rather than having to wait even 30 seconds, a minute, or 5 minutes for a build or a test result. C++ is supposed to be this fast language. We all hear about it. It's the fastest language or one of the fastest languages that's out there. So why are the C++ builds so slow? Why is it so hard to refactor C++ code? C++ was a pretty old language at this point, and it really sucked a lot. So I start Cppclean. So I started as open source, but it was also owned by Google. It was what I call an approximate C++ parser. It was not meant to handle all of C++. It was not meant to be a compiler like Clang or GCC. It was only meant to parse just enough of C++ code so that I could identify cleanup opportunities, ultimately to speed up iteration and improve velocity. And I didn't care about the graceful handling of syntax errors. I didn't care if there were syntax errors. The tool would die, it would go on, things would be fine. And I thought, well, why not use Python? It's really fast and easy to prototype in Python. That way, I could fail fast if I was going to fail, because C++ is an immensely complex language. It was not clear that I could parse C++ using anything. I could have used GCC, but it was very difficult to use at the time as far as embedding an API. Clang wasn't mature enough to really use. It also wasn't fast. I also didn't know it. I knew Python. It had minimal dependencies. I was pretty familiar with it at this point. I've used it for over 10 years now. So why not use Python? But how do I get started? Again, C++ is a huge language. And so what do? So I had heard about generators. I never really used them. I never really got them. But some of the things about generators, in case if you don't know, there's a link there, and you can also go to the PEP 255 for more information about it. But generators are really actually quite simple, and I always was kind of scared of them, and I didn't know if I should learn them. I didn't know what the benefit was. But generators are just a function, but they're a special function. They're a function that behave like an iterator, i.e. it can be used in a for loop. And this means that values can be computed lazily and on demand. And this can help improve performance for CPU or memory, especially memory. If you've got very long lists, rather than building long lists, you can just use a generator to iterate over it, and things are good. And I had heard about them, but like I said, I stayed away from them. But now, I thought, why not try to use generators for Cppclean? Would it make sense? There's an unknown number of abstract syntax tree nodes that can come out of it. When you tokenize a language, there's an arbitrary number of tokens that can come out as you do some of these standard parsing steps. And so I wrote some code that looked almost like this. This was taken from the original check-in, I think, or the original version that I could find of Cppclean. And let me walk you through this code a little bit. It's pretty simple. One thing to note is that it keeps state even after the function seems to exit or yield. And you see a yield in there, and there's actually a whole bunch more yields that were down there, because there's about 10 different cases as I was parsing or tokenizing the C++ code. So just do really simple things. Ignore some white space, try to figure out if I'm getting in an identifier. If I am getting an identifier, get the whole identifier, get the end of a quote if you start a quote, and then go on. You figure out the token type, yield it, return processing to the caller, in which case the caller can then iterate over the tokens. It might need to keep a little bit of extra state about the tokens or not, but this is keeping all of the state of the original source code, so it can yield tokens to make it easier to do the parsing. After doing this code, I finally understood generators and what they were good for. It took me actually doing the work. Without doing the work, I didn't really know what was going on, and that was the problem that I was having. For me, I learned by doing. I can't learn by reading. And so once I actually used generators and I had a problem to use for generators, it wound up working pretty well. And the returning the control to the caller was really very useful when you're doing a parser. So this is what the code looked like, but how long did it take me to write it? Cppclean was actually written in about 2 productive weekend days. So one weekend, Saturday and Sunday. That gave me the entire parser framework. It was probably about 2,000 lines of Python code. Python code is pretty dense, so you can implement a lot in a couple thousand lines. The next weekend was also very productive, and I got the parser working. So at that point, I have a very large code base, the Google code base. I can run my parser or approximate parser on the code base and see how it does. How fast does it perform? How well does it perform? Does it give me the information I want? Can I start building the tools that I want to? Because at this point, I'm still only developing the framework to allow me to develop the tools. But I needed the abstract syntax tree, or ASTs, in order to get there. So I ran it on Google's code base. And what I found was that it parsed probably over 99% of the code, of Google's C++ code. There were some tweaks in there. I had lots of little bugs and had fixes or things I didn't know about C++. And it was very interesting to do C++, implement a C++ parser in Python, because I had to go back and forth between the different languages. Sometimes I'm coding Python, sometimes I'm thinking C++, and goes back and forth. But that was also a lot of fun. And not only that, after a few small performance tweaks, I managed to get parsing of very large files below 1 second. So rather than wait tens of seconds, 20, 30 seconds, a minute to parse using the standard compilers at the time, I could do it in less than a second. I can write a tool if I can process it in less than a second. So even though Python is often considered a slow language in many respects, it actually can do many tasks quickly if you use it effectively. We wound up using Cppclean for many different cleanups throughout Google over the C++ code. It's used in Google Mock. If you've done C++ testing, you might be familiar with Google Mock. It's a mock testing framework. And Cppclean, or the framework for it, is actually used to generate C++ code to make it easier to write your mocks. Both of those projects are open source, and at this point, other people maintain both of those projects as well. I was not very much involved with Google Mock. I was a little bit involved with it in the early days. I was in the same team as the creator of it, but they're both available now. So at this point, it's 2012, Python 2.7 is out. I get tired of being the C++ guy at Google. I go from being Python guy, then C++ guy, and it had been my 4 or 5 years. It was time for a change again. So I decided to join YouTube. That way I could do Python again. I got a chance to work with the guy, Jeremy Hilton, that got me into Google. I knew him through Python. And I started work on the search front-end team. At the beginning, I spent my time ramping up on the YouTube code base. And I needed to figure out what I was going to work on. I did lots of little projects to learn what I could about the system, about YouTube overall. I talked to a lot of the senior engineers and things like that about why they did Python and how they did Python and any problems or sensitivities and things like that. But what am I going to work on? So after talking to a lot of people, I figured out Google likes fast responses from web pages, also on mobile. I like fast responses. YouTube cares a lot about latency. I care about latency. What can I do to improve latency? Can I? So another science experiment. I have to figure out what I can do and how I can do it. But let me describe the state of YouTube when I joined. At the time, all of the web pages were served as one big string based on generated HTML templates. So this implied that all of the back-end communication, all the work that we do on the back-ends, often hitting thousands of back-ends to do searches and things like that, all that work has to be done before you can return any part of it to a web browser or even to the network so it can be sent to the web browser. That means that the browser is just sitting idle the entire time from when it sends a request until the response is received, and mostly received in total. This is an extreme simplification, but it's meant to demonstrate the point of what the code looked like. We would get a request in, we would figure out that it's a search request, we would dispatch it to handle the search request, then we would do all sorts of different work, hundreds of, well, ultimately thousands of lines of code. We would talk to the back ends, and we would figure out what are the responses, how do we want to format this, generate the HTML, and send the response, at which point the caller then just sends the HTTP response along. And that's all fine and well, but again, we're leaving a lot of things on the floor. There's a lot of work that can still be done, a lot of latency that can be gained. So even though YouTube sent everything in one block, it didn't have to be the case. HTTP has something called chunk transfers, where you can send any response in any number of chunks that you want. If you send the responses in just the right way, if you send things like CSS and style sheets and JavaScript, that can be checking to see if those resources also need to be downloaded while you're processing the back-end responses to actually create search results. And browsers are actually set up to do it this way because they don't want to start laying things out until they get all of the CSS, all the style sheets down, because it might change. They might do extra work, they might have to throw it away, not good for latency. And so this meant that browsers and YouTube couldn't be doing work at the same time. So in theory, we could send 2 HTTP chunks for the search results. As soon as we get the request, for static content, we could send the CSS, the style sheets, and JavaScript. And then everything else, all the dynamic content, could come later whenever it comes. The response wouldn't be any slower to the browser, but it would get part of the information faster. And as it does, it could do some of the work. And in theory, this should reduce latency. But the real question is, how much could it reduce latency? And then the big question is, how do I change all of the existing YouTube code to use chunking? At the time, for this path, there was perhaps 1 million lines of code. I can't change 1 million lines of code, certainly not in a reasonable amount of time. And so I need to make this fundamental change. I need to make it safely. I don't think everybody would be happy if all of YouTube went down for hours at a time. So, sorry. So how do I do this? So I thought maybe I could change the code just a little bit. So in a moment, I'll show you the before and after with this code. And you see that now we still handle the search result. And as we do, we check the type of the response. Now, if you remember back at the slide where I was talking about PyChecker, we checked the type there. So dynamically, at runtime, we can check the type, the return result of a function call. In this case, the response could be a string. In the past, it was always a string for all of the different million or so lines of YouTube code. But for the search result, I want to change it to not be a string. I want to change it to be a generator so that I could send the chunks in the for loop that you see there. And then there's the change to break up, instead of one return statement, we have two yield statements. The first yielding almost immediately, doing all the things that it could do statically, very quickly, and then you would yield the rest of the search results. So this is the actual comparison. You can see the pluses. Sorry, I'm losing my voice here. So the one return result becomes two yields, and then there's just that condition and an else statement. No other code needed to change in order to support this. All the other million lines of code, all the other web pages that we serve, while there's only a handful that people typically visit, there are actually hundreds of pages that are served in various different circumstances. None of that needed to change. So what that meant was I could, in theory, still in theory, implement this safe and with less effort, a reasonable amount of effort. So I talked to lots of people. Lots of people are kind of scared by this change because even though in theory it's a relatively simple change, there's still some complexity there. And so I run some experiments, figure out that it's working. I implement all of this. It didn't take too long. I was very happy. I move on to the watch page. This is the big page for YouTube. That's where we're serving most of the responses. It is a video website after all. And I get that going, and it's working very well. No problems with watch, and I'm amazed. I'm very pleased. This is awesome. I got the two big wins. I have one more page that is also high traffic at YouTube, and that's the home page. So I start the experiment on the home page, and it starts running for a while, perhaps an hour or two, and I kick back and relax, because I've already done two. I've done the hardest two. Home is going to be easy. Except that YouTube started serving probably hundreds of thousands of responses of errors after my change went in, and it was tracked back to my change. It started fine, but after a while, things started going haywire. What happened? How could this happen? So I look at the problem. From the actual bug report that was filed at the time, I said, I'm able to reproduce this exception. I'm not sure how it occurs, but I think I can code around it. And the problem was that there needed to be a try finally. And this was implemented in a slightly different PEP that I'll get to in a moment. And so I get this checked in, I try it, it's got to work this time. That was the problem. So I go ahead and I see what happens next. Same thing happens. And I'm like, oh my God, I fixed this problem, or I thought I fixed this problem. Later, a colleague goes on the bug report and he says, you fixed one problem. You didn't fix all of the problems. The outermost stack of generators also needs to be there. While I simplified the code and showed one generator, there was actually 3 different levels of it. And so I fixed a symptom, but I didn't fix the root cause. I need to close a generator in that code too. And I need to make sure that there are no more generators that need to be closed. So I start the homepage experiment for the 3rd time. And this time, it actually does work. And I'm very happy. I don't have to worry about it anymore. What were the results of these 3 changes? This is where the title of this presentation comes from. So a very big number, 600 plus billion. But 600 plus billion what? Well, web page latency is usually measured in milliseconds, and that's the approximate number of milliseconds saved by changing just 3 pages with a relatively simple change. It was billions of milliseconds, which translate to quite a few years, on the order of 20 years, from roughly the same change, roughly a relatively simple change. And the result was people watch more YouTube. I think lots of the metrics that we track at YouTube were better, and I choose to believe that everybody was happier because of this, even though they did watch more YouTube in the end. So what have I learned in all of this? Python has repeatedly surpassed my expectations. Many of the tasks worked well because Python was used to advantage based on its strengths. Python really is a general-purpose tool. It's way more than a toy, unlike my original estimation of Python. It is a powerful tool, and I use it a lot. It's one of many tools. I use a lot of languages and a lot of tools. Tools are neither good nor bad. They provide a different set of trade-offs. So use the right tool for the right job. The more you understand a tool, the more effectively you can use it. The more experience you have, the deeper your understanding for whatever it is. So you need to gain that experience. Now there's a reason why I chose these 3 stories to tell you. I have many more stories with Python and Google and lots of other things. But these 3 stories help demonstrate an important point that I want to make. I started by saying, I'm old. I've seen and done a lot of things over the years. There are some things I've learned that I wish I had learned long ago. And even if these don't make sense to you now, I encourage you to internalize these so that you can become an even better developer faster, especially compared to me. And so these are some of the last things that I want to go through. My time is up, so hopefully I'll take a minute into the question section. But these are the most important things. Value is the only thing that matters. Value is the difference between the cost and the benefits. For the work you do, focus on providing value. Maximize that value. Get the biggest wins with the least amount of effort. Don't worry about the small things. Don't worry about what seems impossible or what other people tell you is impossible. Determine for yourself what is or isn't possible based on your own data, based on data that you can verify. Know what is and isn't important. Scope your solution to the minimum required in order to implement what you want. Focus on your next steps. Know where you're going and where you want to be going. Make sure you're working towards the future that you're trying to achieve and not just shaving a yak. Ensure you have reasonable, but still high, expectations, and make sure that they're in sync with others, because you need to work in a team. Very little work is done in isolation, and as you work in a team, expectations are even more important. And this is my last slide. These are some more general principles. Challenge all of the assumptions and prejudices, especially your own. We all have lots of prejudices. We all have lots of assumptions. We don't think about what they are. It's very important to call out what those are. And use your time wisely. It's precious. It's a limited resource. Use your time to learn. Never stop learning. Always make things better. Do simple things to reduce technical debt when it adds value. And finally, push yourself hard. Try. Experiment. You will make mistakes, but the mistakes you make don't define you. How you handle them is what matters, and that's what counts. Thank you very much.